Okay, so let's we'll take a day in here today, and we'll get back to the lab. And I know people still need to finish up tests, but I want to get you thinking about kind of the next step. And it's nothing. The good news is there's no new calculus here at all. So it's like I know people are still maybe trying to and doing a good job, but still trying to maybe wrap up the 3.1 through 3.6 stuff where there's just a lot of calculus stuff. This is just an application of that. It's nothing new. It's just taking the same ideas we just talked about, but applying them to real situations. And it exhibits why calculus is really one of the reasons it's so useful. So say we got a problem like this. We're given some parameters here, but we need to maximize something. And the section we're talking about now, really from here on out, there's a couple little other minor applications we'll talk about, but mainly it's optimization. Okay, so it means we're going to either try to maximize or minimize some quantity based on some parameters that we're given. So in this case, manufacturer wants to design an open box, so no top on it, having a square base, and that's, as we'll see, that's kind of key here, square base, and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? Now, without calculus, you're sort of at a loss here because there's really not a way to do this. You could just try a bunch of numbers and see what works, but how do you know if you ever get to one that's actually the biggest, right? Calculus, however, allows us to actually pinpoint what is the exact height of this box that's going to maximize volume. And it's probably not surprising that it does this if you think about what we just did in calculus with our tables and our curve sketching and things like that. What we really did was we were able to take a function and, well, in this case, we'd be graphing volume. So let's look at this case. I'm not going to try to be too exact with what the curve would look like, but if I've got volume as a function of height of the box, which we'll call maybe y, maybe it does something like that kind of a thing. Thank you. And so we're trying to find that spot right there, aren't we? Right, we're trying to find the value of y, which is the height of the box in this case, that's going to make the volume. It's a maximum, a local maximum, an absolute maximum, right? And so that's how it's very similar. I mean, it's the same exact stuff we've been doing, only it's just an application instead of just a straight math problem. Okay, so what do we do? Are there any extras to those sheets going around? Did everybody get one? Okay, I got it just right. That's amazing. Okay, so what do we do then? Look, have a glance at your sheet there and just take a look at this. This is your recipe, full 5-step recipe for optimization problems, and what it amounts to is, we're just going to pull one up here too. First thing we're going to do is we're going to draw a picture maybe. We'll draw a picture, we'll assign the variables, and try to kind of get our bearings here a little bit. What are the variables that we're given? What's the variable we're trying to maximize? And so, in this case, a picture might be helpful. It's not, maybe you can do without a picture, but it couldn't hurt. You're going to really see my artistic limitations here. I'm a math teacher, not an artist. Okay, so there's my open face box, open top box. It's got a square base. So what does that tell me?
All the sides are equal.
Okay, so on the base, that's x and that's x maybe, right? What about the height? Is that x? No. I mean, it's possible that it might have the same number, but we don't know that. So the height we have to call something different. Let's call it y. Does that make sense? We have to allow for that possibility that is different.
Since it's an open box and we're just worried about surface area, does the height really matter?
Well, it does. What about the sides of the box?
It's an open box.
Sure, it's open, but what about this space right here?
Oh, I got it.
Right. Okay. So yeah, so we need all the dimensions. Plus we need volume too, right? Okay, now so there's step one maybe, right? Got our variables defined. What's step two say? Thanks. Primary equation. Yeah, we always want to start with this primary equation. That's the one that's being optimized, either maximized or minimized. So what is the question asking us to, in this case, maximize? Volume. So we always got to start with volume. So step two is we need to come up with a volume equation in terms of the variables that we've defined in step one. Okay, so what is the volume in terms of the x's and y's here? Okay, x squared times y. Okay, makes sense? Okay, now here's where we have to pause for a second and ask ourselves, can we do calculus on that function? And the answer right now is no, we can't. We can't because if you look at our book, they don't all say this, but they should. There are different versions, but it says calculus of a single variable. Because that's really what we're doing. In college, you'll extend this and you'll look at multivariable calculus. It's not that much harder, but it's just a little different. But right now, we're focusing on the calculus of functions of a single variable. And so right now, we've got a function of two variables. V is a function of both x and y. And so we need to do something about that. We can only at this point do calculus on this problem and create a curve like this that we can maximize, in this case, if we can whittle this down to two variables. And so that means, take a look at the next step. I think it's the next step, I haven't seen this in a while. Secondary equation, yes, okay. If necessary, so if we do have more than one independent variable, in this case x and y, we have to come up with some secondary equation, or a good name for it. Sometimes it's called an equation of constraint. And that's a good name because the constraint is a meaningful term there. What does it mean? What is a constraint? To constrain something is to hold it back, and so a constraint is something that limits, or
Like limits to one variable.
yeah, limits one variable. It's going to create some practical limits maybe on the problem. Now, what's going to be, and usually when you're looking for the equation of constraint, because it's constraining, it's placing a limit on it, you're going to look for a number someplace. Usually there's going to be a number associated with this. So what is our equation of constraint here, do you suppose? Surface area, yeah, because if, there you go, 108. Now, if we didn't have that, this question wouldn't make any sense. If we're just trying to maximize volume and there are no constraints, well, I got a good answer for you, just make it infinite. And it's, that's, okay, but that's not practical, and so we do have this equation of constraint here. The surface area is to be 108 square inches, right? So what's the equation of surface area for this thing?
5 times.
I think it's just 5 surfaces. I can just add them up, right?
Squared.
So I'm going to get, okay, so surface area is x squared, would be the bottom, right?
Yeah.
Plus
4xy.
4xy. Each of those 4 lateral faces would have an area of xy, and there's 4 of them, right? So x squared plus 4y equals 108. Okay? That's helpful. Now, what do you suppose we could do with that?
So you can x squared, you factor it.
I can factor it. I can do lots of things with it. But now remember what my purpose is. The reason we got this is because our primary equation has too many independent variables. So what I want to try to do is I want to try to eliminate a variable, and the way we do that is by using a variable substitution. I want to come up with a substitution equation. Now you got to kind of really pause and think about this one too, because you can do an awful lot of unnecessary work here and really confuse yourself. You want to be very strategic about this and say, okay, now what's an easy variable to substitute for in the primary equation? And what's also simultaneously be thinking about what's an easy equation or an easy variable to isolate in the secondary equation and see if you can match up those two ideas. Well, really up here, you know, it looks like I could either substitute for a y, probably that would be a good one because it's linear, or maybe even an x squared if I have that opportunity down here, right? Down here though, if I look at the blue secondary equation, it's pretty clear which one I want to isolate. What's your thinking there? Y, yeah. X is not really a good idea because I've got different x terms that are not like terms. How am I going to solve for x there? That's going to be a mess. I've got x squareds and x's. I'd have to set up some kind of a quadratic equation and solve that and get multiple x's and try them. Well, that's a lot of work, and it's, you know, for what benefit? Much, much easier here to solve for y and make that substitution, isn't it? Everybody agree? Okay, so if we solve for y here, aren't I just going to get, what, I get 108 minus x squared all over 4x? Everybody agree? Okay, put a box around that. Always a good idea when you have a substitution equation because you're likely to come back and have to evaluate for y anyway. So this is what we're going to substitute into there. And now we're going to build our new and improved primary equation. Right. We'll have v as a function now of only x's. Okay. So if we do that, we get v of x, and write it that way. Write it as, so it looks like a function, v of x, because that's reminding us that x is the independent variable. So v of x equals x squared times this. Right? That make sense? Okay. Now, we can simplify that a little bit, can't we? Right away, look, we can do some, we can cancel one of those x's, that's useful. And then I could, what could I do? Well, I guess I could pull out the 1/4 and distribute, well actually I don't even want to distribute the x, do I? Because I've already got it factored, right? So I've got v of x actually maybe I do, never mind, I do, because we're going to have to differentiate. So let's distribute the x. I don't know what I was thinking. So we got this 1/4 out front, and then I've just got, if I distribute the x, 108x minus x cubed. Okay. So there is our volume function. Okay, now we're just going to do calculus on this thing. And now we get to a point where we're just going to shift into calculus mode, make a table, optimize the function, maximize the function, find the absolute maximum on whatever interval makes sense. Okay, but that's the last step. The last step that's kind of a little bit different than just what we've done is the domain. When we find the domain of a function like this, there's going to be some mathematical limitations. Anytime I get a function where I get, say, x is on the bottom or something, obviously x can't equal 0 then. So there's going to be some limitations on the domain, potentially, that are imposed mathematically by the function itself. But you also got to remember that this is not just a mathematical abstraction anymore. This is an actual real-world problem, right? This is a geometry problem. And so we also have to kind of think about the reality of the situation here and any restrictions that would impose. For example, given the situation here that x actually means the width of the square base, what's the lower limit of the domain? Well, I mean, I couldn't really have negatives, could I? Because I can't have a negative width, right? And so negative numbers, even though they may be okay mathematically, are not okay physically, right? And so my domain, and in fact, would 0 even make sense? It wouldn't even make sense, would it? And so we can say down here, when we look at our domain, our lower limit would be 0. X has to be greater than 0, right? Now, what's the biggest that it could be? Okay. Okay, now there's where it comes from, it's the 108. Usually it's the equation of constraint that's going to limit things, right? Because without the equation of constraint, this thing could have just been infinite, but it did have a limitation. the limitation was this, right? Was that the surface area can only be 108. And so we can't make X infinitely big because we're limited by the amount of material, by the surface area, right? Okay, now, would you agree here that as X increases, what does Y do? If the surface area is staying constant, it's going to decrease, right? So there's one trick that's very helpful sometimes. If I'm looking for the minimum and the maximum values of X, those are also going to correspond to the situations where we have maximum and minimum Y values, right? And so the biggest X value will occur when the Y value is at its smallest, agreed? Okay. So what's the smallest Y value that we could have? It's 0, right? I mean, if we shrunk, if the base got bigger, but the surface area is staying the same, and this, you have to kind of play like a little cartoon game in your mind here about what's this thing going to do. As X increases, Y is going to shrink. And then the biggest X could get is when that Y shrinks down to 0 and I get nothing but just a flat piece of, flat square on the ground, right? With no sides. So when Y is 0, what would that make X equal to? And I could either look here or I could even look here maybe, right? If Y were to shrink to 0, wouldn't that term go away? And so what's X? Yeah, square root of 108, right? Does that make sense? Okay. And once again, I mean, and I'm not going to say there's a right or wrong answer here. Is the volume, what's the volume going to be when Y shrinks to 0? 0, isn't it? Right? Because the volume, right, the volume is going to be 0, correct? Do you even include that in your domain? I mean, you could. It's fine. You know it's not going to be an answer, though, don't you? So you can either make that square or rounded. It's up to you. They're both, you can argue for both cases, I guess. I'm going to go ahead and make it not include that, being as we know it doesn't work. Okay, but you could if you wanted to. We know that somewhere in between, though, there's got to be a maximum, right? Okay, so there's our domain. Now we just do calculus. And this part, you're getting really good at. So let's just shift, put on our calculus hat, and let's go to the next page, how about? And we'll just do the calculus. Okay, so there's V. So what do we need next? We have the domain, there's V. What's next? If I'm going to analyze this thing with a table. Derivative, yeah. Yes, differentiate V. So V prime. Got my 1/4 out front. Just leave that there. Derivative of the first term? 108. This is an easy one, isn't it? Minus. Okay, piece of cake, right? So if we want to find the critical numbers, the first derivative, then V prime equals 0 when? What? When, no. Okay, good. Yeah, when that factor right there is 0, right? So when 3x squared equals 108. Which would mean when x squared equals, what, 36?
Yeah.
So x equals 6. Now, mathematically, it's plus or minus 6, but we'll just discard the negative, right? It doesn't make any sense. It's not in our domain. So in our domain, it just gives us 6. Okay, now, technically, mathematically, we probably need to show that that's a maximum. Although we'll go back and look back on this and say, that really was unnecessary. Mathematically, how would we do that? Well, we could use a first derivative test, but why not use a second derivative test? The second derivative is so easy to do because it's a polynomial, right? So we could just take the second derivative here. Derivative of 108 is 0. derivative of negative 3x squared is negative 6x, and so my second derivative is just negative 3/2 x, right? Now, the important thing though is our domain only includes positive values of x, right? Right? What's the sign of the second derivative everywhere then? Negative, right? And so you might even, in this step right here, just write negative on the domain, right? So you know it's negative everywhere. So it's always concave down. And so our one critical number we already know is what? It's got, yeah, it's going to be maximum, isn't it? Right? So if I made my table, and the table is almost overkill in this situation. It's such an easy function. Seems like a lot of table for just this one little result. We said we went from 0 up to 10, square root of 1, what was it? Wasn't it square root of?
Yeah, it was. You didn't write square root.
Oh, I didn't. I need to. Should have been square root of 108, right? My mistake. Okay, so. And then 6 was our one critical number, which was a 0 and a negative second derivative, so that makes it a sad face, right? Okay, and that's our maximum. And being as there's only one critical number on the whole domain, when you agree that this function could never turn back around, so you know that it's, that has to be the global maximum. Okay. Now, how could we have argued here that at this point right here, that by just getting that one critical number, that we could stop doing work? And I guess maybe it has something to do with this.
Negative 6 is the your domain.
How could we have said right there that if there's one critical number, okay, well, yeah, we know, okay, good. We know that the endpoints of our domain both give us values of the function that are zeros, right?
If you plug in negative 6, it's not.
Right. How do I know this is a maximum, though? How do I know it's not, without doing any work beyond just finding the critical number? How do I know it's not a minimum? Because the two ways that it might fail to be a maximum would be, what if it were a minimum, or what if it was a critical number that didn't work out to be an extremum? How could we show immediately that both of those are impossible? What do you think? Yes?
You need to be looking for something maximum volume.
Say it again?
You need to be looking for something maximum volume.
Okay.
So if you only have one critical number, it must be the.
Okay, yeah, I mean, that's kind of pushing in the right direction there. We know that, we could argue, I think pretty soundly that we could build some box that has some volume other than 0, right? Agreed? We'd all agree on that. So if we know we can build some box that has some volume other than 0, and the endpoints of my domain are giving me 0 volume, this volume function isn't really that mysterious, is it? This volume function is just a polynomial. So it is smooth, right? What did it mean to be smooth again?
No sharp corners.
Okay, so, and no sharp corners, so that's differentiable, right? And it was continuous, right? So continuous and differentiable, meaning I can draw it without picking my pen off the board. Well, if it's a smooth function, and the endpoints both have 0 values, then is it possible for me to draw this thing starting here and ending there and having some value in between that's positive? Is it possible for me to somehow get to some value in between without having a maximum? Can't do it, right? I can't do it. But if it was a straight line, then there'd be no place with any volume, and we know there's got to be at least some place in there with volume, right? And so we've shown that there has to be at least some place in there with some volume. And how many? So maybe there's more than one, but there can't be, because there's only one critical number. So what's the maximum number of peaks we could get on this interval? 1, because they have to occur at critical numbers. Every maximum or minimum must occur at a critical number. If there's only one critical number, then it has to be a maximum, and there can only be one, right? Does that make sense? And so, honestly, what I think you could do on a problem like this, but I probably won't let you do it first, but eventually what you could do is right here when you get x equals 6, you know, you can just say that's your maximum QED. It just has to, I mean, has to be. Logically, there's no alternative. You know, that's it. Okay. At first, I'm going to make you probably make the table and show me. And we'll get into some problems where it's not that easy, where we're going to get different, you know, we're going to have to actually make a table and analyze it. But in this case, the table is probably overkill. Yep. QED is, I can't remember the exact Latin, but it just means, you know, with algebraic manipulation. It's done. Yeah. It's like the mathematical equivalent of picking up a putt, because it's, you know, it's just so close to, you know, you can just bob it. So I got you. Okay, so let's maybe look at one more quick one, just a little bit different, one that's a little more mathematical. Okay, same, or is less realistic. I mean, this is just a mathematical abstraction of sorts, I guess, but it is an optimization problem, because and that's the word that gives it away. If we're trying to minimize or maximize something, what's the thing that we're minimizing or maximizing in this case? Yeah, okay, but so what's proximity? Proximity. Okay, what's our word we usually use for that in math? We're thinking about the XY plane. And I could even make a sketch if I want to. This is just a downward opening parabola it doesn't just look like this if I graph it. It's just x squared reflected around the x-axis because I'm multiplying by -1, right? And then raised up by 4. So it just looks like that, right? And we want to find closest to the point 0, 2. So there's the point 0, 2. Well, what do we, you know, I mean, who knows where that is? Let's just make this our guinea pig right there. We'll call that XY. What is that? What do we call that in math? Well, you're making this harder than it is. We even have a formula for it that we use in Algebra 1 and Algebra 2.
Oh, yeah.
Distance, yeah, it's just distance, right? Okay, we're just so proximity. We're just trying to minimize distance this time, right? Okay. There's something that comes out of this though that's pretty cool. That's a really good idea that it allow you to make work a little simpler. Okay, so well, a lot of the work's done for us here. Look, they actually gave us. Well, they gave. No, I guess not. We have to set up a distance equation, don't we? Okay, we know what the variables are. We got x and y, and then we're going to try to set up this distance d, right? So what is our distance formula? Yeah, okay, good. So square root, let's write these points down. That one's xy, this one is 0, 2. So what does the distance formula tell us then? What's the distance between those 2 points? I have to call this xy, how come? I could call it x1, y1, I guess, too, but I don't really know what those points are, do I? Right? Those are both variables at this point. But they're constrained variables because x and y are related right there, aren't they? The x, I can't just pick any random x and y value. If I pick an x value, I have to pick the y value that goes with it, meaning the one that fits on this curve, right? Okay, so I've got the distance then is just the square root of x2 minus x1, right? So I just say x minus 0. Right, squared, plus y minus 2 squared. Does that make sense? Okay. I got 2 variables there, though, right? And so what do I probably want to do instead? I can't do calculus on this. I'm really trying to optimize, trying to minimize d, but I've got x's and y's in my function. I've got to substitute. What do I substitute? Yeah, right there. Perfect. There's my substitution equation. This is the recipe, right? Because we have to fit on this function. this tells me how y is related to x, right? So this is my substitution equation. So that's what goes in there, right? And then I just end up getting d equals the square root of x squared plus y minus 2. So what's that going to be?
Four minus x squared. Minus 2.
Minus 2, so that'd just be 2 minus x squared? Squared?
Yeah.
Okay. 2, yeah. Like that?
Yeah.
Okay. And I could simplify this whole thing, right? So, what's that going to give me? 2 minus x squared squared is what? 4 minus 4x squared plus x to the fourth,
Yeah.
right?
Can you just cancel the square root and the squares?
No, huh? Can't. Ah, good. Glad you asked that.
Okay, yeah.
I can't do that because, okay. Okay, that is not equal to a plus b, right? Okay, now I could. Now here's something I could do. This would be if I had that,
Oh, okay, back in my.
then that would equal the absolute value of a plus b. But that's different, isn't it? Right? Because a plus b quantity squared would be a squared plus 2ab plus b squared, which I don't have. See the difference? Okay. Questions on that? Okay. But so if I expand this out, this is just going to give me x to the fourth minus 3x squared plus 4. And you guys check me on that, but I think that's right. Yeah, pretty sure that's right. Okay, so there's D, right? Okay, now this is a little bit awkward because now what are we really trying to find? We're trying to find the coordinates of this point, aren't we? We're just trying to find x and y, agreed? Are we really trying to find the distance?
No.
No, it doesn't ask for the distance. Maybe we don't care about the actual distance. We just want to find the closest point, right? The one that's where the proximity is minimized.
Yeah.
All right. Okay, so we don't necessarily have to use that expression of the distance formula. I've got that square root in there, which is kind of making things a little bit complicated. What if I squared both sides? I could say that d squared equals x to the fourth minus 3x squared plus 4. Wouldn't you agree that when distance is minimized, so is distance squared? Agreed? Okay, when distance is at its smallest value, then the square of distance is also the smallest value it could be. So how about if we define a new function that we'll just call capital D? Yeah, and I don't think the book does this, but this is really a great trick. This is something that you'll do in calculus in the future. Why not? Why not trade a function for an easier function if the outcome is going to be the same, right? Much easier to deal with. Now it's a polynomial instead of a radical, right? Okay, and so there you go, right? We can do calculus on this if I differentiate. I'm just going to get my 4x cubed minus 6x. If I do a second derivative, I just get 12x squared minus 6. Okay, so I could factor that. I could take out what, a 2x, leaving me with 2x squared minus 3. Is that right? Yeah? Okay. So if I find the zeros of this thing then, what do I get? Okay, I get equals 0 at x equals 0 from that factor, or x equals plus or minus square root of 3 halves.
Yeah.
Agreed? Okay. Okay, so let's, well, I have to have a room with that. I'll make my table there. Now this time, are there any constraints on my function? No, none, right? And why there wouldn't be? My x and y, this probably goes forever, right?
Yeah.
So there aren't any constraints. I got critical numbers at negative square root of 3/2, positive square root of 3/2, and 0. Let's just use the second derivative test, how about? My second derivative is right there. If I plug in 0, what do I get for a sign?
Negatives.
If I plug in square root of 3/2, in fact, anything, 1 or bigger is clearly going to give me positives. Okay, so then what does that make these things? Well, these are happy, so those are maxima, or minima, sorry. Right, so that's what I want. This is sad, so it's a maximum. That's not what I want. Okay? And then I'd probably now have to go back, I guess, and just compare the values of these two and see if one of them's bigger than the other. But if we look at our original problem, we don't even really have to do that because it's an even function, right? So we know that this thing, we could certainly do the calculus, but we know this thing has to have folding symmetry about the y-axis because it's an even function, right? And so whatever I get on one side is going to be duplicated on the other. And so the math gods gave us what we expected. We're going to get two of these things. If there's one there, there's got to be one there also, right? And so we know that the x value is the square root of 3/2. If I want to find the y value, I just got to plug it back into my boxed substitution equation, right? Make sense? I guess I'm probably about out of time, but we could easily finish that if we wanted to, right? Okay. So I'll put those. Well, here's kind of the way this will go down. We'll